laws. The drawing shows three objects. They are connected by a string that passes over massless and friction-free pulleys. The objects move and the coefficient of kinetic friction between the middle object and the surface of the table is 0.1. What is the acceleration of the three objects? So you are given three objects here which are accelerating, and because we are told that they are massless and friction-free pulleys, then we can assume that they are accelerating at the same rate. And the data that we are given here is coefficient kinetic, coefficient friction, and we are told to determine what is the acceleration of these objects. So now we have three masses here. We have one on the left, and this one we can name it M1, and the one in the middle we can name it M2, and the one on the right we can name it M3. If we assume that mass 3 is moving downward or is accelerating downwards, then it means that M2 is accelerating towards the right because it is being pulled down, and the M2 then pulls this M1 upward. Okay. Let's look at the tensions. We can name the tension on the right hand side as T2, so that the tension on the left hand side be our T1. Now, because M1 is accelerating upwards, let's look at the total forces that are acting on M1. Now, the first thing we're going to do is to look the total forces acting on M1, because we need to start with mass 1. So the total forces acting on M1, number one, is the weight 1. Now weight, if this is our object M1, there's that weight of it acting downwards due to gravity, and weight is given by mg. So we're gonna say W1, which is mass 1 times g, and m is the mass of the object, which is 10 kilogram, and g is the pull of gravity or acceleration due to gravity, which is acting downwards, and that's given by 9.8 meters per second squared, and that's going to give us 98 Newton. Another force which is acting on M1 is the tension, and it is acting upward, and we'll name it T1. If we can then relate to second laws of motion, which says F is equal to ma. Now we can then say our T1 minus W1 is equal to the horizontal, which is ma, but then we will put here 1 to signify for the mass 1. This a is the acceleration at which it moves. We want our aim is to determine this acceleration, because we have been told that it is massless. Okay, and this can be written as T1 minus W1 is equal to ma, and this can be written as T1 minus W1 we have found to be 98, so we're going to say minus 98 Newton is equal to mass is 10 grams, so it's going to be 10 times a acceleration, so it's going to be 10a, and this one we can give it to be our equation 1. Number 2, we can then look on the forces which act on mass 3. We're going to look mass 2 later, because mass 2 is being affected by the two tensions. So if we look at the forces which is acting on M3, we still have the T2 and M3, and if this is our object M3, still we have W3 which is acting on it, and this given by mass 3 times the force of gravity. So if we're to consider first W3, which is a force acting on mass 3, which is given by mass 3 times g, and this is going to give us 25 times 9.8, and that's going to give us 245 Newton. And then another force acting on this M3 is the T2, so we can equate the same vertical forces to the force due to second law of motion. Then we can say W3 minus T2 is equal to M3 times G, and this is going to give us W3 is 245 Newton minus T2, and this is going to give us is equal to M3 is 25, so we're going to have 25A, and this is going to give us 25A. Sorry, this is A and not G, the acceleration. This is A, and this is going to be our second equation. So now, after looking this, we can then check the forces acting on M2, and that's the third thing. Forces acting on mass 2. Mass 2. Here we looked on mass 3, M3, and here we looked on M1. Now, if you look at force mass 2 looks like this, and there are kind of like 4 forces acting on it. We have the T2 acting on it. Sorry. We have also T1 acting on it, and we have W, which is the weight which is acting on it, and this is W2, which is given by M2 times G, and also there's normal force acting on it, which is Fn, and there's also kinetic friction, which is Fk, which is acting on it. So we can have horizontal forces here and vertical forces here. So in M2, we can start by looking at W2, which is going to be the mass, which is 80 kilogram times 9.8 meters per second squared, and that's going to give us 9.8 times 80, 784. So this is going to give us 784 Newton. Then we can then proceed and say that, and our Fk, which is acting on it, Fk, kinetic friction, is given by coefficient of kinetic friction times normal force. This normal force is the same as the weight that we have got because they are acting on the opposite side. So our kinetic friction, we can find it by multiplying the coefficient of kinetic friction, which is 0.1 given. So we're going to give us 0.100 times normal force, the 784 Newton, and that's going to give us 78.4 Newton because you have one decimal place. So yeah, and then we can now equate these two forces and say then T2 minus T1 minus W2 is equal to MA. That if we have T1, the tension, the force on the tension 2 minus the force on tension 1 minus weight of the object or force due to the weight will give us mass times the acceleration, and it's this acceleration that we are looking for, and this is going to give us T2 minus T1 minus W2 we have found to be 78.4 Newton, and it's going to give us M2 is 80, so it's 80 times A, and this one we can call it equation 3. So let's wrap to create more space. So now we can write these equations, and so we can proceed and say write the first equation, which is T1 minus 98 Newton is equal to 10A, and this one can be written as T1 is equal to 98 Newton plus 10A, and this can be the first one. So the second one we can write T2 from here is equal to 245 Newton minus 25A, and this is going to be our second. And the third one we can write from here T2 minus T1 minus 78.4 Newton is equal to 80A. So we can then proceed and put equation 1 and equation 2 into equation 3. We can then replace equation 1, this one, and equation 2, this one, into our equation 3 by saying T2 minus T1 minus 78.4 is equal to 80M. And what is our T2? T2 is 245 Newton minus 25A, that is our T2, this one, minus T1, minus T1, and T1 is 98 Newton minus 10A, then with minus 78.4 Newton is equal to 80A. So from here we can collect the legs term. We can then proceed and say 245 Newton minus 25A minus 98 Newton minus 10A minus 78.4 Newton is equal to 80A. And we can collect them together and say 245 Newton minus, or it is 245 Newton minus 98 Newton minus 78.4 Newton minus 25 minus 25 minus 25A minus 10A minus 10A is equal to 80A, and this one is going to give us 245 minus 98 minus 78.4. This is going to give us 68.6. 68.6 is going to give us 35A is equal to 80A. Then we're gonna 686, 68.6, because this is a minus. If it crosses the other side, it becomes a positive, and it's going to give us 111, because when this is a minus, it crosses the other side, it becomes a positive. So we have positive 115A. So we can proceed and then calculate the value of our acceleration by saying 68.6 is equal to 115A, and we divide both sides by 15. Divide both sides by 115. Our acceleration is equal to 115, and our acceleration is equal to 0.596 meters per second squared. So this is the acceleration of this object. So the first thing that you need to do is to give this object or masses names, and then identify the types of forces that are acting on each and every force. You have a balloon, and it's a hot air balloon. What we normally know with hot objects, that they are less dense and therefore they will be lifted up. So this balloon weighs a mass of this. So the first thing we can do here is to write the masses that we have, or data. The data that we are providing with is mass is equal to 500 kilogram, and network or work net is given to be 9,700,1234 joule. And we have been told also that the balloon have a speed, so velocity is equal to 8.0 meters per second. So this is the data that you are provided with. We are told that this balloon is moving, taking off from rest. So when taking off from rest, then it means that V initial is equal to 0 meters per second, and therefore this is our VF. So whenever you are told that it is moving from rest, it means that the initial velocity is 0 meters per second. Say to rest, final velocity is equal to 0. So the question says, at what height above the surface of the earth does the balloon have a speed of this? So this balloon starts moving from a point like this, and it goes to this point. Okay, so then if we apply work energy theorem, which tells us the total net work done is equal to the mechanical energy. So if we say then work net, or the total net work done, is equal to total mechanical energy, or change in mechanical energy. And change in mechanical energy is the change, or the sum of change of potential energy plus change in potential energy, because at a certain point, at this point, we have maximum potential energy and minimum kinetic energy. But then it starts to move, it means that this potential energy is converted to kinetic energy, and as it goes until this point, when it reaches here, then our kinetic energy is converted to potential energy. So we need to look both the potential energy at this point and kinetic energy at this point, and we look at the change in both. So we can say then work net energy is equal to the change in kinetic energy plus the change in potential energy. So let's start with the change in kinetic energy, which is the kinetic energy final minus kinetic energy initial. And kinetic energy, this is going to be, I'll put this one like this, and this one is going to be change in kinetic energy will be half mvf squared. This is the formula for kinetic energy, minus 1/2 mass of the object vi squared. And we have been told that it starts from rest, or if it starts from rest, it means that this velocity is equal to 0, and therefore change in kinetic energy is going to be 1/2 mvf squared, because velocity is 0, meaning that the whole of this term is going to be 0, and going to leave us with the value or the magnitude of the final velocity, which is going to give us then 1/2 times the mass of the balloon, which is 500 kilogram, times the velocity at which it was moving, and that is 8 meters per second, and that's going to give us a value of, that is 250 times 64, and that's going to give us 16,000 joule. 16,000 joule. So this is the change in kinetic energy. Let's look the change in potential energy. The change in potential energy is going to be the potential energy final minus potential energy initial, and this is going to be potential energy is given by mass of the object times the gravity acting on that object, which is 9.8, because this is a constant, times the height. So in this case it is y2 minus mg y1. y1 is the initial height. Now if we proceed and say then change in potential energy is going to be, now at y1 you realize that at point 1 it was at the ground level, so the height there was equal to 0, right? Yes, the height there is equal to 0, and therefore we are going to say that our mgh, change in potential energy, is going to be mass of the object times gravity times the height in y2, which is the height that we are looking for, and this is going to give us mass is 500 kilogram times 9.8 times y2, and that's going to give us 500 times 9.8, and that's going to give us 4,900. That's going to give us 4,900 y2 joule. So this is the change in potential energy. So let's go back to this equation so that we can find this missing height. We have said that work net, which has been given to be 9,097,000, so it's 97,000 is equal to change in kinetic energy, and change in kinetic energy we found to be 16,000 plus change in potential energy, and change in potential energy is 4,900 y2, because we are looking for this. This one and this one is the same, so we can take this to the left hand side and say 97,000 joule minus 16,000 joule is equal to 4,900 y2, and on the left hand side we are going to remain with 81,000. We are going to remain with 81,000 joule is equal to 4,900 y2. So from here we can divide both sides by y2. We can divide both sides by y2, so that we get, so divide by 4,900, and we get the height as, so y2 is equal to 16.553 meters. So this is the height at which the balloon reached. At what height above the surface of the earth does the balloon have that speed. So it means that if we were to measure or take a skeleton of this, it means that after height of 16 meters above the sea level, so 16 meters 5.3 above the sea level, that is the height at which our balloon had a speed of 8.0 meters per second. The first thing here to look at is to know that the network, according to work energy theorem, which states that the total network done is the same as total or change in mechanical energy, and change in mechanical energy is given by change in potential energy plus change in kinetic energy. And then from this equation you can work one-on-one until the final. Three forces are applied to an object as indicated in the drawing. F1, force 1 as a magnitude of, so we have a diagram and there are two forces acting on it. We have F1, F2 and F3, which is like the resultant and is directed, so F1 as a magnitude of 21 Newton and is directed as 30 degrees to the left of the y-axis. So it means that if this is 30 degrees, this is 90 degrees, so it means that this angle is 120 degrees. Force 2 has a magnitude of 50 Newton and points along the x-axis, so it means that this angle is 0 and its magnitude is 50 Newton and the magnitude of force 1 is 21 Newton. Alright. What must be the magnitude and direction specified by the angle in the drawing of the third force F such that the vector sum of the three forces is 0 Newton? So if they say that the vector sum of the three forces is 0 Newton, then we can equate the two forces. F1 plus F2 plus F3 is equal to 0, and this is the same as saying F3 is equal to minus in bracket F1 plus F2. Alright, so let's look at these forces into their own components. If you look, these forces, they have their components as X and Y, which is in this case force F1 and F2. So let's start by F1. F1 make this angle, so we can look at force 1 in the X component, and that's going to be the magnitude of F1, which is F1 cos theta, and that's going to give us 21.0 Newton cos theta. Here is 120 because it makes this angle to this. It's going to be cos 120, and that's going to give us 21 cos 120, and that's going to give us minus 10.5 Newton. And F1 in the Y component is going to give us F1 sin theta, and that's going to be 21.0 sin 120, and that's going to give us 21 sin 120 degrees, and that's give us 18.19. That's give us positive 18.19 Newton. The same we can look for F2 in the X component. F2 in the X component is going to be the magnitude of F2 times cos theta, and cos theta here is 0. 0 is 1, so it's meaning that in the x-axis is going to be 15 Newton, and with the Y component it's going to be F2y, which is going to be magnitude of F2 sin theta, and sin 0 is 0, so 0 times 15 is 0, so it's going to give us 15 Newton times sin 0, which is going to give us 0 Newton. From here we can then look at the resultant of the X components, which you can say Rx. R is the resultant, meaning that the sum of all the X components, which is going to give us F1x plus F2x, and that's going to give us F1x is minus 10.5 Newton plus F2x is 50 Newton 15 Newton, and that's going to give us 15 minus 10.5, and that's going to give us 4.5 Newton. That's going to give us positive 4.5 Newton. And the resultant of X is going to be this is Y, cos 1Y plus F2Y, and that's going to give us F1Y is 18.19 Newton plus 0, and that's going to give us 18.1 Newton. So after doing this, we can then proceed to look at the magnitude of F3. Remember, we did say F3 is equal to minus F1 plus F2. So it means that F3, magnitude of F3x is equal to minus Rx, and that's going to give us minus 4.5 Newton, because we did find Rx as 4.5, and F3 in the y component is going to give us minus Ry, and that's going to give us minus 18.19 Newton. So these are the components of F3. So from here we can find the magnitude, which is going to be the square root of F3 in the x component squared plus F3 in the y component squared, and that's going to give us minus 4.5 squared plus minus 18.19 squared, and that's going to give us everything 4.5 squared, and that's going to give us 20.5 plus 18.19 squared, 330. This is 330.888, and that's going to give us, so we'll bring everything here, plus 2 0.5, and that's going to give us 351.37, and the square root of that is going to give us square root of answer. It's going to give us 18.75. So this is the magnitude. So this is the magnitude of the force. So now when they say calculate the direction, direction is the theta now in which it makes with this angle. So we can then calculate the theta it makes with that angle and say that, okay, theta is equal to tan inverse of y over x, and in this case our y is equal to minus 1 of 18.19 over minus 4.15. So this is tan inverse of that, and that's going to give us tan inverse of 18.19 divided by 4.5, and that's going to give us 76.10 degrees. So it tells us that this angle here is 76. Okay, but if you want to know the angle from here until this point, then you can say 76 plus 180, and that's going to give you 256. So this angle here is going to be 180 plus 76. That's going to give us 256.1 degrees. However, the angle theta that it gives us with this one here, the one that you are told to calculate, is this one here, 76. So this angle is 76 degrees. So that's how you approach such questions and then solve it. I hope this tutorial help you in preparation for your test and the exam in the future. So the first thing to do is to write the forces into their components, all forces in x and y components, and then you look at the resultant forces, meaning that you are going to find the sum of all the x components and the sum of all the y components. Then you equate them to this equation that we did right here, and then after that you can look for the magnitude, which means that the square root of each component squared plus another component squared, and that square root will give you the magnitude. And for you to find the direction, you find the tan inverse of y over x. Thank you so much for watching. See you next time. Bye.